We are back with section 5, and we're going to recognize molecules and polyatomic ions that do not obey the octet rule and draw reasonable Lewis electron dot structures for them. Although the vast majority of molecular compounds and ions obey the octet rule, there are some exceptions. These include molecules and ions that have fewer than 4 pairs of electrons on that central atom, or that have more than 4 pairs. Molecules with less than an octet include Bf3. Boron is kind of that key element that has 3 outermost electrons, so it's happy to be full at 6. And molecules that have more than an octet, and that's when the valence shell, when that energy level is greater than 3, because d orbitals are available to accommodate some extra electrons. Here's when you can see that there's more than an octet, PCl5. So off of that central phosphorus, there's 5 chlorines. And off of that sulfur, there's 6 fluorines. Here's that boron trifluoride, Bf3, and you might look at this and go, oh, there's not an octet, but this would be an exception. And here's boric acid. Everybody else is satisfying that octet except for boron, and that's okay. Here are some Lewis structures that have more than that octet. Elements that are in that third or higher periods form compounds and ions where that central atom can be surrounded by more than 4 electron pairs. They still have the same number of electrons if you do that electron count. Though, if I said, oh, sulfur has 6 electrons and fluorine has 7 electrons times 6, so we need to add up all of those and account for all of those electrons, that will still follow that rule. Let's sketch the Lewis structure for ClF4 minus. First, I'm going to do my electron count. Chlorine has 7 and fluorine has 7, but we need to times it by 4. And it's a -1 charge, so then we need to add 1. So 7 times 4 is 28, plus 1 is 29, plus 7 is 36 electrons. Let's have my Cl, and I'm going to have 4 F's around it. And I'm going to start by putting 1 bond between each of those. So that would be 2, 4, 6, 8 electrons. Now I'm going to fill up my fluorines to give them an octet. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. I still have 4 more to go. So 33, 34, 35, 36. So around my chlorine I have 4 bonded pairs and 2 lone pairs of electrons. That's more than the octet, and that is okay. Here is looking at it in a little bit neater fashion. We can see here is my chlorine with 4 fluorines around it. Each fluorine satisfies the octet. And again, look at my central atom. I've got chlorine has 4 bonds and then those 2 lone pairs around it because I had to have those 36 electrons. And I forgot to put the brackets around with the -1 charge on the outside, so don't forget to do that. Let's sketch the Lewis structure for ClF2 plus and ClF2 minus. Can you try that? First, let's do our electron count. 7 for chlorine plus 7 for fluorine, and there's 2 of them, so 14. And then it's a +1 charge, so that means it lost an electron. So -1 would give me 20 electrons. Here I've got 7 plus 14, so that's 21 with a -1 charge, so I need to add an electron, 22 electrons. Let's figure out how these are arranged. I put a bond in between the chlorine and the fluorine here, and this is our +1. And I need to get to 20 electrons, so I've got 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And for the -1 charge, again, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So off of the central chlorine atom, I have 2 bonded pairs and 1, 2, 3 lone pairs, compared to the +1 ion, I only have 2 lone pairs around that chlorine. This next section is one of my favorites. We're looking at molecular shapes. We're going to use the valence shell electron-pair repulsion theory to predict shapes of simple molecules and polyatomic ions and to understand the structures of more complex molecules. Lewis structures show how atoms are connected in molecules and polyatomic ions, and hopefully you're feeling pretty confident about those Lewis structures. But Lewis structures are two-dimensional, and molecules are 3D objects. The three-dimensional structure is absolutely critical for understanding molecules and their function. And this VSEPR theory is based on the idea that bond and lone electron pairs in the valence shell of an element repel each other and seek to be as far apart as possible. Let's look at the importance. Carbon dioxide is a linear molecule. We have drawn carbon dioxide. We know it's linear, at least on paper. But this means that in 3D, if it's a linear molecule, the carbon dioxide molecules are nonpolar and will not be very soluble in water, which is a polar solvent. Water molecules have a bent structure. This is one reason why water molecules are polar and have properties such as cohesion, surface tension, and hydrogen bonding. Knowing the molecular geometry helps scientists to understand the shapes of more complex molecules like proteins and DNA. The shapes of these molecules play incredibly important roles in determining the jobs performed by these molecules in our bodies. Let's think about an atom here. Atoms are surrounded by clouds of negatively charged electrons. And when you have atoms in a molecule that are close together, these electron clouds repel each other. Think about electrons and electrons, negative and negatives, repel each other. Because of this repulsion, the molecule will automatically adopt a particular geometry so as to allow all those atoms to be as far apart from each other as possible. Think of these electron clouds as magnets of like charges. The closer you push those magnets together, the more potential energy they have. And things want to be at the lowest energy possible. So if you let go, they will push apart, lowering their energies. And atoms will do the same thing. VSEPR, that term that we saw, is valence shell electron-pair repulsion. It's when a molecule can be described in terms of the distribution of the bonding atoms around the central atom. And we can describe a molecule in terms of electron-pair geometry and molecular geometry. We have to draw the Lewis structures before we can predict the shape. And we will first describe the electron-pair geometry, then we will describe the molecular geometry. The electron-pair geometry is the geometry assumed by all of the valence electron pairs around a central atom, both bonds and lone pairs. This is different than the molecular geometry, where we will describe the geometry of the central atom and the atoms directly attached to it. It's important to recognize that lone pairs of electrons on the central atom occupy spatial positions, but their location is not included in the verbal description of the shape of the molecule or ion. This is a little cheat sheet that you will be able to use. I will explain it more as we get going, but it is a tool that you're going to want to be able to understand. Here is another one helping us to see linear compounds, trigonal planar, if it's bent, if it's a tetrahedral, trigonal pure metal, all of these. I'm going to show you how to use them in just a minute. Here's some more. Again, we'll come back to this. How do we get to that shape? Well, Lewis structures tell us, again, how many atoms and bonds there are, bonding pairs, are connected in a molecule, and the lone pairs. The 3D shape is determined by its bond angle, so simply by how many atoms are attached to it. Let's look at the Lewis structure of CH4 right here. When I draw it out on paper, obviously it's flat. And it looks like there's 90-degree angles in between these hydrogens, but there's not. In 3 dimensions, it's been experimentally found that those angles are 109.5. Well, if that's the case, then it can't be planar. This methane molecule must be 3D because the sum of 109.5 times 4 is definitely greater than 360. So to accommodate the 109.5 bond angles, the atoms adopt a new 3D geometry to minimize the repulsion between atoms, and we call this structure a tetrahedral shape. That hydrogen atoms fit at the corners of a regular tetrahedron shape with the carbon at the center. I'm going to go back to this chart and show that looking at our valence electron pairs that we had 4 bonds, so our electron pair geometry is a tetrahedral. And that puts us into this bracket. So how many bonding pairs did we have? We had 4 H's and no lone pairs. So it is a tetrahedral shape. You're going to hear the word electron domains. And a domain is a region where it is most probable to find regions of electrons. That could be an atom. So in that last CH4, off of that central carbon atom, we had 4 domains, 4 atoms off of it. And a domain can be a single, a double, or a triple bond, and that all is describing one domain. A domain is also a lone pair. That counts as one domain. For example, if I looked at water, H2O, and I wanted to draw this, I would first do the Lewis structure, and I'd say, okay, I have 6 electrons for hydrogen, 1 each for hydrogen, so that's plus 2, so I gotta have 8 electrons. I'm gonna have my oxygen, I'm gonna have 1 H, I'm gonna have a second H, so that's 1, 2, 3, 4. I need 5, 6, 7, 8. If I'm looking at water, I would have 1, 2, 3, 4 domains off of my central atom. Of those 4 domains, 2 of them are bonding atoms, 2 of them are lone pairs. Let's go back to this chart. I had 4 domains off of my central atom, so its electron pair geometry is tetrahedral. But I had 2 bonding atoms and 2 lone pairs. Again, the lone pairs are this column. So my water molecule is bent. Even though the way I drew it in my Lewis structure, it looks like it's linear. That's okay. It doesn't matter how you draw your Lewis structure. Your Lewis structure can look however you want, but in 3 dimensions, that's telling us what it's actually going to look like. We can also use this chart. It's going to tell us the same information as the other one. We would look at this. Electron pairs up here, our total for water was 4. And within that 4, we said we had 2 bonding pairs and 2 lone pairs, giving me, that would give me a bent structure. And this is what our molecular geometry would look like. I would have an H connected to my O, connected to an H, and I'd have these 2 lone pairs of electrons up there. Let's look at some rules for predicting those molecular or ion shapes. First, most important, you need to draw the Lewis structure. Then we count the number of electron domains around that central atom to determine the arrangement, minimizing repulsion. We describe the molecular geometry in terms of arrangement of the bonding domains. And remember, double and triple bonds count as one domain. So for example, we've drawn CO2 now a couple of times. And I'm not going to put the electrons around the oxygens right now. But we would look at this molecule and go, okay, this is one domain, this is 2 domains. So this would have 2 domains. Let's go back and look at our chart. If we have 2 domains, and of those 2 domains, 2 of them were bondings, pairs, and there was no lone pairs, that would be a linear compound, and it would look like this. In order to predict molecular shape, we assume the valence electrons of each atom in the molecule repel one another. They want to be as far apart from each other as possible. This compound, for example, the electrons that are surrounding the oxygens here and the electrons surrounding the oxygens on the left, they are wanting to be so far apart from each other that they are as far apart as they can be, 180 degrees, making it that linear compound. And for water, when we were looking at that with 2 lone pairs, whenever there are lone pairs, they actually require more room than bonding pairs and compress the angles between bonding pairs even more because they are space hogs. Those electrons are almost like supercharged and wanting to be really far away and push those atoms even further away. We're going to look at some examples with different numbers of domains around those central atoms. So 2 domains or 2 things around a central atom. That would give us a linear shape, 180 degrees. Beryllium chloride, for example, if I drew that Lewis structure, I would be able to look at beryllium and go, okay, there's 1, 2 things around beryllium chloride. Off of CO2, okay, there's 1, 2 domains off of CO2. In HCN, there's 1, 2 domains off of that carbon. It doesn't matter if there's a double bond or a triple bond. We're looking at how many objects are off of that central carbon. So these are all linear structures. Again, this is showing us how to use that. If I have total of 2, and of those 2, two bonding atoms, giving us a linear structure. Let's look if we have three things around a central atom. My electron geometry for 1, 2, 3 things should be trigonal planar. And this would be an example of if I've got CH2O, I have 1, 2, 3 things off of that carbon. Again, it's trigonal planar. So of those three things, they are all three atoms. Let's go back and look at our chart. I have two options. If I have three total electron pairs, if they are all three bonded atoms, then I have a trigonal planar geometry. But what if I have two bonded atoms and one lone pair? I would have a bent molecule. See how if I have one lone pair and two atoms, that lone pair is going to push those two atoms down. It's not going to be linear with those two atoms. It's going to be bent because those lone pairs push those two atoms away from each other. Here would be an example of a molecule, SO2, that has two O's off of it. This one is a double bond, this one's a single bond, but off of that S I have a lone pair of electrons. So that would be a bent structure. Notice that if I have three atoms, they're 120 degrees from each other. But if I add that lone pair, remember that's a space hog, this is going to be a little bit smaller than 120 degrees. It's actually about 116 because that lone pair is going to smush these two just a little bit in closer to one another. What if I have, of those three atoms, a double bond? So instead of this being a single bond, single bond, single bond, and being 120 degrees each, this double bond is actually a place where there is more electrons. So it's a greater electron density. So that will also affect my bond angles. Instead of 120, again, this is going to act kind of like a lone pair, and it's going to push these two chlorines a little bit closer together. So they're not 120, these are actually 111, and that would be 124 degrees. So it's not quite equal, like this compound here where I've got this double bond. It's not going to be 120, 120, 120. This is going to push it and make that 124. Make that bond angle a little bit greater. Like I said, those lone pairs are physically larger than atoms, and their repulsions are greater than atoms. In CH4, we said that those bond angles were 109.5 exactly. And if I add a lone pair of electrons, for example, an NH3, that pushes that 109.5, so these three H's are now 107 degrees because this takes up a little bit more room than that one hydrogen did. And in water, with two lone pairs, it pushes that 109.5 to the 107 to even smaller at 104.5. Here's just another tool showing us that if I have three domains, the two options of shapes that I have. My electron geometry is trigonal planar, but if I have 0 lone pairs, it's still trigonal planar. And if I have two atoms and one lone pair, it's bent. Moving on to 4 things around that central atom, if my electron pair geometry tetrahedral. If all 4 things are atoms, it is also a tetrahedral. What if one of those 4 things is a lone pair? Then it becomes trigonal pyramidal for molecular geometry. If there are 2 lone pairs, it becomes bent. And this just shows the molecular geometries for 4 electron pairs. If I have 4 atoms, it's tetrahedral. 3 atoms and 1 lone pair is trigonal pyramidal. 2 atoms and 2 lone pairs is bent. And this just shows us some more examples of tetrahedral shapes, trigonal pyramidal, and bent. And here is just another example looking at our Lewis dot structures of 2 different bent molecules, but the electron geometries are different for both of these. Notice I have 1, 2, 3 things. So this electron geometry would be trigonal planar. Off of water, I have 1, 2, 3, 4 things. 2 atoms, 2 lone pairs. Both bent structures. Angles are going to be a little different though. Looking up at 5 electron pairs, the electron pair geometry for 5 is trigonal bipyramidal. Now the molecular geometries, depending if I have no lone pairs 1 lone pair, 2 lone pairs, 3 lone pairs. It can be all of these different shapes: trigonal, bipyramidal, seesaw, T-shaped, or linear. And same with electron geometries. If it's octahedral, that means that there's 6 things coming off of that central atom. And if I have 6 things with no lone pairs, this is my octahedral shape. If I have 1 lone pair, it's square pyramidal. And if I have 2 lone pairs, it's square planar. And here's just another tool to help us figure out which molecular geometry it is for 5, and this one is for 6. Now let's do a bunch of practice. Let's look at SiCl4. If I drew the Lewis structure, counted out how many electrons I needed to account for, this is what I would get. Then from there, I can say, okay, I've got 1, 2, 3, 4 domains coming off of silicon. And those 4 domains, there are 4 atoms. So I would have an electron geometry of a tetrahedral and a molecular geometry of a tetrahedral. What about these two? Let's draw our hydronium ion, H3O+, and ClF2+. Again, first, draw the Lewis structure, see what you get. Here's what I did for H3O+. Hydrogen each has 1 electron, and there's 3 of them, so 3 electrons there, plus 6 from oxygen, and has a +1 charge, so I'm going to subtract 1, giving me 8. All right, I have oxygen with 3 hydrogens coming off of it. That would be 2, 4, 6 electrons, so I need 2 on top. That would be 1, 2, 3 atoms and a lone pair. So that is 4 things coming off of it. My electron geometry would be tetrahedral. Of that, I have 1, 2, 3 atoms and a lone pair, which would be a trigonal pyramidal. ClF2, hopefully you got that off of that chlorine there was 2 lone pairs and 2 atoms. So its electron pair geometry would be tetrahedral because there's 4 things coming off of it. 2 atoms, 2 lone pairs would be a bent structure. How about CH2Cl2? Pause the video here and try to build it. Our Lewis structure should look like this. So there are 4 domains coming off of that carbon, and they are all 4 atoms, so it would be a tetrahedral. How about SF4? SF4, so my sulfur with 4 F's coming off of it. If I counted up all of my electrons and had 8 electrons off of each fluorine, 8, 16, 24, 32, I would still need 2 more electrons to come off of that sulfur. This would be one of those exceptions to the octet. So there'd be 1, 2, 3, 4, 5 things coming off of it. Its electron pair geometry would be trigonal bipyramidal, and there would be 4 atoms and 1 lone pair, which would give me a seesaw shape. Try building ICl4-. If I added up all of my electrons, that I would have 4 chlorines coming off of it. So that'd be 8, 16, 24, 32. But if you did your electron count, there should be 36 electrons that we have to account for. So that would be 2 sets of lone pairs. 4 atoms and 2 lone pairs. Its electron geometry would be octahedral. Its molecular geometry would be square planar. Try building ICl2-. I would have 7 electrons from iodine, 7 from chlorine times 2, that would be 14. It's a -1 charge, so add an extra electron. I need to account for 22 electrons. Off of my iodine, if I put 2 chlorines, and I surrounded those chlorines with lone pairs, so 2, 4, 6, 8, 10, 12, 14, 16. I still need to get to 22. 17, 18, 19, 20, 21, 22. So off of iodine, I have 1, 2, 3, 4, 5 things. It would be trigonal bipyramidal. And if I look under trigonal bipyramidal, 2 atoms and 3 lone pairs would be a linear compound. Try drawing PCO4+. Did you get a tetrahedral shape? Try drawing PCl6-. And you should get this, which would be an octahedral. Draw xenon tetrafluoride, XeF4. Do your electron count. We should have those 4 fluorines off of xenon. And if you do your electron count, you still have 4 extra electrons to count for. So there would be 2 lone pairs and 4 atoms. So that would be octahedral electron geometry and square planar for molecular geometry. Try PCO5. The molecular geometry and electron pair geometry would be the same here, trigonobipyramidal. We have 10 joining questions to finish off this section. Take a minute, pause the video. Hopefully you got bent. Take a minute and pause. There would be 3 lone pairs. Pause here. 1 lone pair. Pause here. Should be 120 degrees. Pause here. Should be 109.5, and the second one would be a little less than 109.5. Would be 180 degrees. This would be 90 degrees at an octahedral shape. This would be 180 degrees. CLF2, its electron geometry would be tetrahedral, but those lone pairs, remember, that's not going to be a 109.5 angle because those are space hogs, so it's going to be bent but less than 109.5. It would be a linear compound. Hopefully this is what you got when you drew it out.